to make scatter plots and best fit lines. So our first example shows a table, and this table shows the average life expectancy of people in the United States between 1900 and 1990. So in the year 1900, the average life expectancy was only 47.3 years. And you can see as time goes on, up until 1990, the average life expectancy was 75.4. So what I want you guys to do is go ahead and plot the points. The year 0 is going to be 1900. So at 1900, we're going to put a dot somewhere around 47.3. What's our scale on our graph here? Are you sure it's by tens? Well, yeah, this would be 55. So this would be 45. It just starts. See that? You see these little two hash marks? Those two hash marks give the graph permission to not start from 0. Okay, so then we have 65 here and 75, etc. Okay, so I'm going to put my first dot, about halfway in between 45 and 50 for 47.3. It's really approximate. Then for 1910, we're right at 50. That's handy. For 1920, we need 54.1, so I'm going to go pretty close to 55. For 30, it's 59.7, so I'm going to go just under 60. 40, 62.9, which is pretty much 63, so I'm going to go halfway between. 50 is 68.2, so, or I'm reading the wrong one. Did I do 50 yet? No, 68.2. About halfway. 60 was just under 70. Then 1970 was just over 70. 1980 is going to be halfway, maybe a little past half. And 90 was just under, or just over rather, 75. So what we want to do is now take a straight edge, and what you want to try and do is draw a line that would have the same number of points above as below the line. So write that down. Same number of points above and below the line. And it is approximate, you guys. We're not all going to have the same exact line. And it's okay if it varies a little bit. But you want to try your best to draw a line that would have the same number of points above and below. Okay, so let's see what we come up with.
Does it have to start at 0?
And no, it shouldn't start at 0, you guys. Yeah, starting at 0 is not a prerequisite. No. Well, it just depends on the data. Let's see, I got 3 under, 3 over. Let's see, this looks pretty good. Well, that actually wasn't that good. Trying again. Okay, my line's fairly decent. So our next thing to do, that we have what we're going to call our best fit line, is we're going to pick 2 points on the line. And once again, we're going to have to kind of estimate. Okay? Now for the purposes of our notes, I want you to pretend like your best fit line is exactly the same as mine and use the same points that I'm going to use. Okay? So I'm going to look at my line, and it looks like I have something close to an intersection there. So that's the point 50, 65. And let's see, do I have another point that looks somewhat close? Well, I don't have anything great. I'm going to use this one. And that says in 100, what year is 100? 2000, good. Comma 80. This is approximation. So when I'm checking your work for this type of problem, when I'm checking on a test, I'm really going to look at, how well you just tried, how well your line is fitting the points, and then that you chose points that were somewhat on the line, and then that you found the slope of your points, etc. Okay, so now turn it over, and we need to transfer those points, the same points that I used, on the other side. So 50, 65, and 100, 80. And the first thing to do is to determine the slope of our best fit line. Yes?
Should we use the numbers that you used even if they don't match up with ours?
Yeah, use the numbers that I'm using, even if it doesn't match, just so our notes will all be the same. Okay? Maybe make a note to yourself. So finding the slope, 80 minus 65 over 100 minus 50. So we get, what is that? 15 over 50. Very good. 3/10. Then it says, what does it tell us about life expectancy? Jack?
Every 3 years, the life expectancy goes up about 10 years.
Okay, what did Y represent? Y was life expectancy, and X was time, right? So I think what you meant is every 10 years, life expectancy goes up about 3 years, okay?
Yeah.
Or it increases by 0.3 years every year. Good. So we can write that. Every 10 years, life expectancy increases by 3. Now, it says, what is the L-intercept? Well, notice on our graph that they labeled the y-axis L. So when it wants the L-intercept, it really wants the y-intercept. And let's find it algebraically. So we're going to take our slope of 3/10 and one of our points. I'm going to use, it doesn't really matter, I'll use the first one. So we'll say, I'm going to use y equals mx plus b this time. And replace y with 65. Our slope of 3/10, our x of 50 plus b. Go ahead, cross cancel. 10 goes in 1, 10 goes in 5. Then we end up with 65 plus 50, or equals rather, 15 plus b. And we get an approximation of 50 for our y-intercept. Now, our graph looks like it crosses fairly close to 50, at least mine does. So we're pretty on target. So now we can give our equation, except instead of L, instead of x and y, we're going to use n and L. So I'm going to say L equals what? Who can write the equation for me? Lauren?
L equals 3/10 n plus 50.
Good. Very nice. So now we're going to use that equation to answer a few questions. 5A, when life expectancy will reach 100 years? Sorry, that seems to be phrased weird to me. So, where are we going to plug the 100 in? For L or for N? L. We want life expectancy, or L, to be 100 years. And work backwards to solve for N. Subtract 50 from each side. Multiply by the reciprocal. And nothing will cross cancel, unfortunately. So we have 500 over 3. But 500 over 3 is not really a year. So let's actually divide 3 into 500. We'll just approximate. If we need to do long division, we can. 3 into 5 goes once. 3 into 20 goes 6. So about 166. The 6 would repeat, right? So 166, is that a year? No.
Oh no, it's 1900 plus
1900 plus 166. So what year is that?
2066.
Yes, approximately the year 2066. Man, I hope I live to see 2066. You guys probably will. Well, if I do, let's see. If I'm 100, oh, I might just miss it. Dang it. I would, according to our line, I would live to see 2066 if I would be 100 in that year. Oh, my goodness. Actually, I might make it. I definitely will make it. Awesome. Life is good. All right, so now we're going to use our equation to go backwards and figure out what was the life expectancy in 1800. All right, what was n? Who can figure this out? What is the value of n if it's the year 1800? If n is the number of years after 1900?
Negative 100.
Oh, negative 100. Good. You guys all figured it out. So we're solving for L. And we have 3/10 times negative 100 plus, what was it, 50. Cross cancel. Let's see, negative 30 plus 50. Oh no. Perhaps our slope is a little steep. L equals 20. Oh man, they're all goners. I think 20 was more like the life expectancy during really ancient times. So perhaps our slope is not quite right. Oh man, poor people in 1800. How did they ever even, I mean, how did they start the country if anyone lived past 20? Founding fathers, I'm pretty sure were older than
What would
that.
happen like when the person like
Okay, so our line's not perfect. I was hoping that the 100 was great. That was working out in my favor. And you know, this probably is not a linear relationship. Like in the last 100 years, life expectancy has gone up dramatically because of what?
Medicine.
Medicine. We take better care of ourselves. We eat more nutritious food. All of that. So it's not truly a linear relationship, but nonetheless. Lastly, we're going to use our best fit equation to estimate when life expectancy was 65. So where am I going to put the 65? Henry?
L.
Yes, we're going to put it in for L. Good. Go ahead and subtract 50 from each side. Multiply by 10 over 3. Yay, it cross cancels.
1950.
Yeah, so if n is years after 1900, then the year was 1950. That doesn't seem too far off to me. I think it's been more consistent in the 20th century, but as we go backwards, like we said before, it didn't really go up at the same rate. All right, good job, you guys.